The Clean Power Hour is brought to you by CPS America, the maker of North America's #1 three-phase string inverter, with over 6 gigawatts shipped in the U.S. The CPS America product lineup includes three-phase string inverters ranging from 25 to 275 kW. Their flagship inverter, the CPS 250-275, is designed to work with solar plants ranging from 2 megawatts to 2 gigawatts. The 250-275 pairs well with CPS America's exceptional data communication, controls, and energy storage solutions. Go to chintpowersystems.com to find out more.
But the reality is that the adoption of this technology is inevitable because it's the lowest cost form of energy. And it's no different than the adoption of single axis trackers, where it was inevitable because it was the lowest cost form of energy. And so it's just a matter of time until all the module providers recognize that and ultimately sign up to this technology.
Are you speeding the energy transition? Here at the Clean Power Hour, our hosts Tim Montague and John Weaver bring you the best in solar, batteries, and clean technologies every week. Want to go deeper into decarbonization? We do too. We're here to help you understand and command the commercial, residential, and utility solar, wind, and storage industries. So let's get to it. Together we can speed the energy transition.
When you think about ground mount solar, you either think fixed tilt or tracker, and increasingly tracker. Certainly that is the case here in North America. But there's a third alternative now, and that is flat to the ground solar. You heard me right. I know it sounds a little wonky at first, but after you listen to this interview, I think you will be convinced that there's a there. My guest today is Jim Tyler. He is a storied energy professional. He was the vice president of EPC at First Solar. He was the co-founder of DEPCOM. And now he is the CEO of a company called Erthos that is revolutionizing utility scale solar. Welcome to the show, Jim Tyler.
Thank you, Tim. It's fantastic to be here.
The Clean Power Hour is brought to you by DynaWatts. If you're a solar PV asset manager or performance engineer, you need better data and better business intelligence. With DynaWatts' digital twin benchmarking technology, you get more accurate, efficient, and faster performance measurement results. The 4th generation Dino recently completed a technical review by DNV. You can download the report at dynawatts.com. That's DENOWATTS.com. Now back to the show. I'm a geek for racking. And you're trying to do away with racking, though, Jim. So this is truly a disruptive technology that you have innovated, and I look forward to bringing this to our listeners. Solar is growing at a unsurpassed clip, right? 90% of new energy on the grid is wind and solar now, and we're just getting started, really. The easy part is cleaning the grid, but it's an important part of the of decarbonizing the economy and stepping back from the brink of climate change. And I know that you are a mission-driven entrepreneur, but give our listeners a little bit of your history. You'll have to keep it short because it is very storied.
Sure.
And then let's get into what is Erthos and why is this a compelling product. But give our listeners some background on yourself, Jim.
Sure. I definitely appreciate the opportunity here, Tim. Really, the beginning of my experience in industry was in food processing. And in food processing, a tremendous amount of energy gets used. And I did many, many things with steam in that world of food processing. But I really got into the solar industry in about 2005. There was several companies, but in particular, I started working on projects where there were thin film solar manufacturers in the Silicon Valley. It was really the very beginning of these concepts of utility scale solar, companies like NanoSolar and MioSoleil. And I was designing machinery to help manufacture that equipment. I became aware of the industry at that time. And then in 2007, I became aware of a company called OptiSolar, which really was changing the nature of the industry. In my opinion, they had gone out and secured thousands and thousands of acres of land and interconnect queue positions in the state of California and helped facilitate the renewable portfolio standard in the state. And I had the opportunity to go to work at Opti to build their manufacturing facility in Sacramento, and then head up the EPC group at Opti with the first solar plants built in Sarnia in Canada. 2008, along with everybody else, I the stock market crashed, and Opti was a venture capital funded company, and venture capital dried up, and First Solar had the opportunity to come in and get a tremendous group of people and a fantastic set of projects. And I was one of the few that got an opportunity to go across at First Solar and start to build their EPC division. And what a luxury, just to be paired with so many incredible, talented people at that organization. As the market grew, First Solar grew, had huge volumes and installation capacities that we were doing at the time. And then the market really started to shift, and the technology of crystalline silicon just got better and better and better. And I had a colleague tell me one time, never bet against silicon. It's one of the most studied materials on the planet. And that was really very true. And they have really done tremendous things to bring the cost of solar down. And so in 2014 or so, went across and founded Depcom Power with a couple of colleagues, and grew Depcom to what it is today. It's one of the top EPCs in the country. But really started to recognize, it's the same thing over and over. You keep bringing these technologies to bear, and I had done just about everything you could do within the industry, from the EPC, the manufacturing, developing projects. And I was riding my bike one day and just said, well, what would happen if the solar panel, the price of the solar panel were free? It seems like an odd question, but when I started, the solar panels were $5 plus a watt. And when I exited in 2018, they were 27 cents a watt. And there's a very real answer to that question. Economically, it makes sense at about 50 odd cents a watt to put the solar panels flat on the ground. It's just the nature of the economics of how things work within the product. And so that idea happened in 2019. And that's when I really began to look into the intricacies of what would it take if you said, okay, yeah, that works financially. Does it work technically? And that was the impetus of the advent of Erthos back in 2019. So.
I mean, it is incredible. It's almost too good to be true that the cost of solar, has fallen more than 90% since, say, 2013. And all the while, the technology gets more efficient. You mentioned First Solar with their thin film technology, still a major player in utility solar. And then, a slew of polycrystalline competitors nipping at their heels, so to speak. But the industry is driven by the financeability and the cost of installation when we're talking large-scale solar. And so that is one of the compelling things about Erthos to me, is that you're achieving an LCOE, a levelized cost of energy, that is perhaps 20% lower than other technologies on the market. And I want to talk about why that is, and what are the pros and cons of making this innovation. There's always trade-offs with any technology, but why did nobody do this before you, Jim?
Those are great questions. I've been asked that question many times. Having been in the industry myself, all the way through from the very first fixed tilt systems, thin film, with First Solar, and then the crystalline silicon, and then moving to trackers from fixed tilts. If you hearken back to around 2010-ish, that type of a time frame, pretty much all solar that was being installed of utility scale was being installed fixed tilt. And while there were several companies that were looking at doing trackers, including First Solar, we acquired one of them. ATI was looking into it. Nextracker came along right in that time window. There was quite a few companies. SunPower had their own tracker. The dilemma the trackers provided a financial advantage. They did. Right around 2010, as the price point of the solar panel continued to drop and the technology of the trackers got better and better, the efficiencies rose, it made financial economic sense to move to a tracker. And however, there was a huge number of risks. What's going to happen with the bearing? What about harmonic dampening and stuff? I mean, are the modules going to be able to sustain when they're up at 60-degree tilt angles? There's all these variables. The variable of inter-row shading and just dozens and dozens of variables. But the reason trackers, they finally said go, is because the economics drove it forward. The levelized cost of energy is the sole driver. It's the price of the electricity that matters, because the buyer is the utility. They buy the electricity. They want the cheapest price they can get. And so as the industry moved forward in those early years, 2008, 9, 10, and those PPAs started to change, it was always about the price of the electricity. And so trackers had a financial advantage over fixed tilt, and they started to be adopted, even though the risks were huge in comparison. There was no contest. And then over a period of 7 years, trackers went from 0 market share to 70% market share of the US, driven by one variable: the cost of electricity that comes out of the plant is cheaper, even though there was more risks and other things associated with it. And we've all seen the pros and cons, and I've installed many of them personally. I'm a big fan of many of the different tracker technologies and companies that have come out. So it's simply a question of the economics of the levelized cost of energy that matters. And when you introduce a new technology, whether that's a new tracker or a new module, pick whatever the new technology, you have to get that technology adopted. And there's early adopters. The early adopters are typically the most financially constrained projects. They're the most underwater. They're most pressured to try to get that new technology adopted. They take those initial risks. And then as the technology gets adopted and the banks start to become familiar with it, the industry starts to become familiar with it, it just starts to grow naturally on its own, because the power purchase agreements that are being signed by the utilities are based on price. And so there's a natural draw to reduction in the cost of electricity that drives the industry forward. And Erthos is simply the next step in that reduction in the cost of electricity. Now, you asked a second question: why didn't anybody think of this before? Because the reality is it made financial economic sense at about it depends on geographic location, but about 47 to 51, 52 cents a watt. Well, we crossed that threshold in 2017, 2016 timeframe. Well, there were companies that were doing something. There was PEG and there was 5B, which were doing a high density solar, all pressed together, still held up off the ground, but it was high density solar. And they saw those economics. They saw that shift. And so all Erthos did is take it to the last stage, put it all the way to the ground. And that putting it all the way to the ground, it totally eliminates all the steel, 35 tons of steel per megawatt. Just think about that number alone, 35 tons of steel per megawatt. And we're going to put in 23,000 megawatts of solar in the United States this year. That's a massive shift. I mean, think about how much steel you're talking about and the amount of energy it costs to make all that steel, and all the labor it takes to install it, and all the transportation costs to get it there. You eliminate all of that, it just changes the economics dramatically. Dramatic shift in economics. But there's a lot of headwinds to the technology. You got to get these various people, companies, and industries to say yes. And that's what we have been doing over the last 2 years since we announced our technology, is getting through that technology adoption process.
So let's address some of my initial skepticism, okay? I worked for a large EPC in Northern Illinois. I saw the switch from fixed tilt to trackers, it was like a light switch being flipped. It was like all of the designs from the developers we worked with went from fixed tilt to tracker overnight. And then we never looked back for anything a megawatt or above for ground mount, right? And that's true today. It's even more so. Now, if you go to Canada, things are different, right? At very high latitudes, trackers lose their advantage. But here in the Great Lakes, certainly trackers are the technology of choice. But when you put solar panels on the ground, they are going to be more exposed to some elements like water. We have a very flat landscape here in Illinois. Illinois used to be a giant swamp, basically, or a wet prairie, to say it more romantically. But and so drainage is a major concern. And so when you submerge a solar array like that sends up red flags for me. How do you account for that? Can solar arrays sustain being submerged?
So when I first began this process, I was concerned about two things. One of them was temperature, maximum temperature of the module, and the other was water. Those were the first two things that were of concern to me. And before I ever said, let's go hire people and go ask other people to invest, I wanted to prove to myself that those two things were viable. And so began the research on those two fronts. So with regards to water, interestingly, that problem, I became aware of the process of manufacturing solar panels when I was working at First Solar. There is a process where you submerge the solar panel in water, it's in an electrolyte, to run a test. It's called it's effectively a leakage current test where you put full sunshine on it. But I was really surprised when I saw that. I'm like, it didn't really dawn on me that a solar panel could be submerged. And then I started, discussing it with the various people that colleagues of mine at First Solar, and they said, "Oh yeah, they're completely waterproof." And we think about energy or we think about module performance over time. And if you go back in time into 2004, 5, 6, 7, 8, damp heat was the number one category of degradation, the thing that caused things to degrade faster. And everyone was putting effort and energy into solving damp heat because it was the bane of everybody's existence. So the edge seals and the materials of choice for the connectors and so on and so forth, they just got better and better and better. And so when you think about a solar panel that has to be out in the rain permanently, it's effectively, whenever it rains, it's not underwater, but it's exposed to a tremendous amount of water. The natural thought is that a solar panel should be completely waterproof. But when you say, I'm going to physically put it underwater, people go, oh, you can't do that, right? There's a mental break that engineers often have. But the reality is it's no different than a piece of wire. A wire has an electricity running through it, but we bury wire all the time. There's just insulation around the wire to prevent the electricity from getting out, or AKA the water getting in. Solar panels, the same thing. It's a great big insulated wire, and it's got insulation all around it. And so it turns out of all of those parts of insulation, the plastic parts are the susceptible part. Well, plastic absorbs water over time. Well, solar panels are generally rated to IP68. IP68 means 1 meter submerged for 24-hour rating. We've done a lot of testing on this subject. They can go underwater for a lot longer than 24 hours at a meter. But the reality is that solar panels, when you put them on the ground and when it rains, you don't go design solar plants where there is a natural floodplain. It's not generally good practice for anyone to build a solar system in a natural floodplain.
Right.
But when it rains and you get 2 or 3 inches of water, and then that water runs off and it goes into the ground, the reality is the solar panels, they'll be underwater for a short period of time, and they're very, very shallow water. And that depth duration is actually the metric or the variable that matters. And so we have what's called a a depth duration spec that the solar plant is designed to a 500-year storm event, which limits the depth duration combination to the number associated with the IP68 rating. And it turns out it works quite well. And people just don't, it's hard for them to appreciate that solar panels are actually waterproof. So.
And what about the balance of system? What about the connectors and, potentially junction boxes, things like that? Can they also sustain being submerged?
They're as an object, the plastic parts, just like the plastic or the insulation on a wire, all of those materials are made to be immersed in water. And the subject of interest is the rate with which the water goes into the plastic and changes the insulation resistance of the plastic. There's actually a term called leakage current in all solar panels. And there's an allowable amount of leakage current according to spec. When you change that insulation resistance a little bit, it allows for a slightly higher leakage current. But there's natural protection devices built in that they're like circuit breakers. They turn off when the leakage current gets too high. The inverters protect for things of that nature. But what we have found through now over 2 years of operation of the first plant we installed, even after it's gone through 2 years and it was in California with all those crazy rainstorms, we've proven that leakage current subject is a non-issue. It's a trivial result relative to the losses that you can expect. I think we're losing 0.5% of the energy as a result of leakage current losses in our first plant, which is all things considered, when you look at the total energy production, I think our first plant is running at 90, creeping up on 99% performance index. That's all losses included, like soiling losses and shutdowns, grid connection issues, you name it, it's all losses combined. And that first plant's running at 99% of performance index. Typical industry, they'll run at 93% of performance index. So we're proving without a doubt that the solar panels can be set flat on the ground and perform the way they're supposed to and not degrade. Actually, not just not degrade, they're degrading slower than we predicted.
Yeah, I want to talk about that. I want to talk about the degradation. Walk us through, though, before we talk more about that and the overall performance, walk us through a typical installation. What are the parts and pieces, so to speak, of an Erthos array, so our listeners can understand this? Just paint us a picture, if you would.
Sure. Well, for those of you that are familiar with the industry, you put solar panels are sitting up on racks, whether they're fixed tilt or trackers. We physically eliminate all of the steel from the plant, and the solar panels are sitting on the ground. The frame of the solar panel is in physical contact with the dirt. All the solar panels are sitting side by side, edge to edge, end to end. There's a cable, an aircraft cable, 1/8 inch diameter aircraft cable that spans through a series of holes in the sides of the panels that are installed in the sides of the panels. And those cables, all they do is tie the solar panels to each other so they don't move vertically relative to each other. The cable's not tensioned or anything like that. The cable runs out to the boundary of the array and it goes through a little concrete block. And then the concrete block sits on the ground, and then we connect the cable to the concrete block. And that runs through every single panel in both directions. So you can think of it as a big mesh of flexible mesh made out of solar panels that's sitting flat on the ground with a concrete perimeter block protecting it from things like erosion, water erosion that might want to go underneath the panels and things of that nature. That concrete block performs that job. So it's a very, very simple set of parts: the solar panel, the steel cables, the concrete blocks, and then the DC connectors that go from the solar panel strings all the way back to the inverters. Now there's a magic trick that occurs with all of this. And I learned this lesson when I was at First Solar. We had we had the world's least cost electron at First Solar with the solar panel, and that solar panel was patented. And so we were taking a industry leading position as the solar module manufacturer, patented lowest cost technology. We're going to design standardized plants. And we developed standard shapes and sizes for arrays and inverter sizes and racking spacing and so on and so forth. So we got really, really close to being able to standardize, kind of like an Apple an Apple Mac computer versus a computer of the PC-based computers. Erthos, because we've patented the solar panels on the ground, the fundamental underlying technology of how it's assembled, we get to control the standards with which you design the plant. And that's what we've done. So we've standardized the fundamentals of the design with string level inverters. And when you do that, you're able to standardize many aspects around the plant. And that standardization facilitates further reduction in cost of those components that you'll ultimately use, because you get to use high volume of those standardized components. We were on the precipice of being able to do that at First Solar, and then crystalline silicon passed, and lots of inverter technologies come along. But with Erthos, because we have those patents, we're able to control those standards and reduce that cost to an absolute minimum threshold. So it's a very powerful part of the underlying technology is that standardization. And so all the cables and the hardware, the physical, those are all through marketplace that we've been developing with our suppliers and the supply chain that feeds all of these parts and pieces. Right?
The Clean Power Hour is brought to you by CPS America, the maker of North America's #1 three-phase string inverter, with over 6 gigawatts shipped in the U.S. The CPS America product lineup includes three-phase string inverters ranging from 25 to 275 kW. Their flagship inverter, the CPS 250-275, is designed to work with solar plants ranging from 2 megawatts to 2 gigawatts. The 250-275 pairs well with CPS America's exceptional data communication, controls, and energy storage solutions. Go to chintpowersystems.com to find out more. So there's a couple other advantages that immediately spring to mind. The speed of installation, the amount of labor and time involved in installing a solar array, and then the O&M. So talk about the installation and the O&M for these types of installations.
So having installed, I think I was up to about 8 gigawatts of personal that I was involved in, capacity and volume over my career with First Solar and DEPCOM. There's a very important metric that we always used, which is man hours per megawatt. How many man hours did it take to install 1 megawatt DC per plant? And it was very accurate at predicting on a given project what that man hours per megawatt would be. Through the initial analyses, we determined that it would take about 1/4 of the man hours per megawatt to install an Erthos system than it would to install let's say a Nextracker tracker system, modules, grading, everything all inclusive. So for every 100 man hours for a tracker-based system, it would take us about 25. Now, that's when you get to scale. So with the very small projects we've done, we're running down at about 30 to 40% of that total volume. But at the end of the day, because you removed all of the racking, all of the steel, all the pile driving, all the underground cabling, you've cut the links. There's no row spacing between arrays. You've cut the links between the inverter stations like less than half. So all the cable that you run in the AC is less than half. All the trenching that you got to do for all of that. There's just so many places where the labor is reduced. And as many of your listeners know, labor is one of the highest risks for any solar plant. And the construction is that labor and the time duration to build the plant. If you have to build a plant in Mississippi through the winter, it's a real difficult place to do that. Mississippi mud's kind of rough for those that have done it. And by cutting the land use in half and the time to build more than in half, with half the number of people, all of those risks are reduced. Are there still risks there? Of course there are. but the relative risk to building a tracker plant on the same location is dramatically changed because you're disrupting less land. You're not having to drive piles in all the ground. All of those variables change. So it's a huge impact is the labor pool required drop. When you move into the O&M, like you were saying, that's another thing. If you don't have any racks to worry about, that's one of the component costs of O&M. There's another big one, and the image behind you with your setup, it doesn't really show it, but a lot of solar plants have a real issue with grass. Grass is growing up and in between the panels, and they've attempted to automate grass mowing. It turns out grass mowing is a very expensive O&M part or O&M component, just mowing the grass. Well, not only do we have half the land is covered by 92% solar panels, and the other 8% is the roads. So there's almost no grass associated with the solar plant at all inside the fence. So while there's minor things to do, it's really not a variable. So that one alone dramatically reduces the O&M cost, the variable part of O&M cost. You remove the trackers, that one's gone as well. So our total O&M price comes down. I think we're about 30% lower O&M aggregate all in versus an equivalent tracker plant of the same size. So
you mentioned the footprint of the plant being half. So if I hear you correctly, 100 megawatt plant with trackers, we would assume 5 acres per megawatt, 500 acres for a 100 megawatt plant. With Erthos, you're suggesting that you could squeeze this down to 250 acres. Is that right?
230 to be exact.
Okay.
So yes, if everything is apples to apples, you just take a regular site, whatever you can. A tracker plant generally is going to consume about 5 acres per megawatt. There's a lot of variables that go into that. That's a big random round number. With Erthos, it's not a random round number because the ground coverage ratio is always basically going to end up at 92%, just because of the nature of the beast. Whereas with trackers, intra-row spacing matters. It might be 17-foot rows, but in some locations, you might want to get all the way up to 21-foot rows based on inter-row shading and elevation shifts and all these other variables that are quite complex to analyze. With Erthos, it's flat. There's nothing to analyze. You put it flat.
The only caveat there, I guess,
design process.
The only caveat there, Jim, I guess, is that you're going to use a higher DC to AC ratio with Erthos because the panels are flat to the ground, right? So you're getting a lower insulation value. What is that preferred DC to AC ratio? Let's say in the desert Southwest, in Southern California or Arizona.
So roughly speaking, based on the price of solar panels today, let's say a solar panel that you can buy your panel for 35 cents a watt. Just big round number, pick a number. The DC-AC ratio in the Southwest of the United States is going to be roughly 1.75. That'll be the optimal DC-AC ratio, okay? As the solar panel price drops, the price of the module goes down, the DC-AC ratio is actually going to go up. As the price goes up, the DC-AC ratio is going to go down. So there's an interplay between those two. And then depending on where you are geography, if you're in Northern California versus New Mexico versus, let's say down to Florida, you'll actually use higher DC-AC ratios down in Florida, for instance. Odd, but that's the reality of an optimized site. So anyway, so that's the reality. But as the solar panel price gets lower, you're basically using more panels to do the same thing that a tracker was doing. So the solar panel guys love it, right? You're going to build a gigawatt AC of solar. You're going to do 1.8 gigs DC versus 1.3 or so from a tracker plant. So you're just displacing who's getting paid. It's the module companies that are going to be making the money rather than the tracker companies.
Right. So you've gotten some projects under your belt now. What are the reactions so far from your developer partners or IPP partners? What objections do they have, and how are the projects going so far?
Yeah, so great question. So just like you take if you go, like I said, harken back to 2011, before trackers took off, in tracker design started happening in 2008, 2009. So they started doing their very small test plants back in that point in time. That is where Erthos was 2 years ago. We were installing our first test plants. So now you progress forward. We've got 7 test plants in operation. We've proven energy yields. We've proven performance prediction. We've proven the robotic cleaning of autonomous robotic cleaning. We've proven all these variables that we knew we needed to get done. And now you're putting your projects, the developers, they're putting in bids, right, for RFPs. Only they're using our technology in the bid for the RFP. The first of those bids started a year ago when they started putting in bids with our technology. So those RFPs are starting to come true, and people are starting to win RFPs with our technology in it. So that's the critical variable. Once you've won a bid with our technology in it, the price point that you won, the next guy, what is he going to bid? If you got 5 competitors into the same RFP, who's going to bid what price? And if you're able to reduce your LCOE price that you're bidding into that RFP by, let's say, 5%. I mean, theoretically, you could move it all the way down by 20%, but you don't want to do that, right? You want to keep a lot of the money as a developer. You want to keep your money in your own pocket. So you reduce by 5% or 6%, you win the bid. Your competitors, your developer competitors, they go, well, how did they win that bid? How did they get their price that low? There's only one way to get the price that low, and it's to use an alternate technology. So that developer now has to go in and bid his next round. Now that technology slowly gets integrated into the process of bidding. We're in that process right now. So to date, Erthos has right up at 200 megawatts of projects under contract. We're getting ready to install our first call them 5 and 8 megawatt scale projects, so significantly larger footprints, various installed locations around the country. I think by the end of this year, we'll have 8 or 9 megawatts of those plants installed. But the big ones, the ones at 20 megawatts up and the 100 megawatt and up, we have one contract that many people may have heard of on a 100 megawatt project in Texas. And so that project is under contract. We have several more 100 megawatt projects that are approaching contract for us. And it's just it's the process that you have to go through get that technology adopted. And we are absolutely in that chasm right now, getting ready to cross over that chasm to the larger scale projects being adopted.
Yeah, you referred to a 100 megawatt project in Texas. That's with Industrial Sun. What is the status of that project?
That project is in its development cycle. So it's an interesting part about the Erthos business model. People often think of us maybe as like a tracker supplier, or they think of us as an EPC, 2 key aspects of the industry. And in reality, we're neither of those. We are a technology provider that provides some materials, but not all. But we're the engineer of record for the developer. So, but when we begin the engineering cycle, we begin that cycle very early on in the development cycle of the project. Typically, the engineer, the developers, they might hire a Black & Veatch or a Burns & McDonnell or one of the engineering firms to support their development cycle. They'll hire us to support their development cycle. So that's a bit of a shift in the concept. So we start at that very early stage. So in the Industrial Sun project, we're in those stages. So land control, interconnect, we're assisting them with all of that aspect, the power purchase agreement, all of those things. We're assisting them through those cycles in the development of those projects. Unfortunately, they, along with everybody else in the country, are constrained by the interconnect queue cycle times, and it's hitting everyone. And that project is not immune to it any more than anybody else's project. And so the lead time to getting the project online and built and so on and so forth, I mean, in Texas, you can get permits fairly quickly. The interconnect queue is the sole long pole in the project. We would be able to go to guns today if the interconnect queue is available. But we all know that's a universal problem for all the speed limit by which our country is bound to install new solar into our grid. And it's a huge problem because it was, 4 years ago, we were doing interconnect queues were 2 years long. Now they're up in 4-year timeframes. And that's just a massive, I'm not the expert at that. I've done it a lot, been involved in a lot of projects, but that problem has to get resolved for us to help facilitate a faster adoption of solar and wind and so on into our electric grid. So.
Yeah, major pain point for the solar industry.
Yeah.
I want to talk about solar modules. You are working with a variety of solar panel makers. What is the process that you go through to onboard those companies? And then let's talk about module reliability and degradation, because that is a unique story to tell with Erthos.
So fundamentally, part of our business model is we create what we're calling a solar marketplace, where various companies that provide certain aspects of the technology are licensed. We are licensing our technology to them, and so we have a contractual relationship. So the module is now 65% of the cost of the total cost of the plant is in the module itself. So it's obviously the key variable that we have to look at. So I think we have 9 of the tier 1 module providers in the world are signed up to our module licensing agreement. So if the marketplace is going to be filled with all of these module providers, and Erthos is pushing our technology of putting modules on the ground, we have to do some level of qualification of the module provider, right? So that's an important piece. So a simple statement, tier 1, that's easy. Just straight up tier 1. That's you've got to meet that criteria to be considered. But we push the module through further review aside from that before we are comfortable with that module provider, us signing up that module provider to our contract. Now, we don't control who is the provider of the module on the project. The developer does that. They sign the contract with the module provider, but the module provider has a contract with us around the intellectual property that's associated with the module. So we help to facilitate getting that marketplace in order. And so far, we've got, like I said, 9 of the tier 1s under contract. Several of the others are they're ready to go. They want to see adoption of the technology, and they want to play the wait and see game because they're the biggest ones in the industry. But the reality is that the adoption of this technology is inevitable because it's the lowest cost form of energy. And it's no different than the adoption of single axis trackers, where it was inevitable because it was the lowest cost form of energy. And so it's just a matter of time until all the module providers recognize that and ultimately sign up to this technology.
So early in the interview, you said your 2 main concerns were heat and moisture. Yes. Why is heat a concern, and how does that play out for modules that are flat on the ground? What are the pros and cons of putting modules flat on the ground?
Yeah. So heat was frankly my number 1 concern, because I already was aware of the water side of the equation, but it was difficult to understand if you're going to put a solar panel on the ground, is it going to get too hot for the maximum allowable temperature? I live in the desert Southwest in Phoenix. And so I literally built a plant in my backyard to do some initial concept testing to prove it. And it turns out, and the physics actually makes sense once you've done and proven these tests, but if you put a solar panel on a rack up in the air, there's a certain rate of heat dissipation that the air will do of the solar panel. If you take that exact same solar panel and put it on a roof, on the roof of a house, and let's say it's 2 or 3 inches off that roof, there's a certain heat dissipation that the roof and the air cooling around that module on the roof bring. Those two extremes, those are the boundaries. The roof-mounted solar is what actually is the trigger of the maximum allowable temperature for the solar panel, which is like 85 degrees C. And it turns out that if you put a solar panel on the ground, on the dirt, it's almost exactly halfway between the temperature you would find on a roof and the temperature you'd find on a rack. The variables are 29, 22, and 15 is a term of a variable that's in the energy calculation. But nonetheless, when you put the solar panel on the ground, the temperature, the maximum temperatures that it sees are almost exactly halfway between what you would see on a roof versus a rack. Since we figured that out, it became a moot point because rooftop is everywhere in the world and they don't have any problems. Degradation, all those types of issues are managed because they've figured out damp heat. You go put a solar panel on a roof in Florida, you've got damp heat as hard as any other place in the world, right? You put a solar panel on the ground in Phoenix, damp heat is fundamentally, it's not an issue as it turns out. So that was the temperature problem. But turns out there's a bunch more variables that lead to degradation. People think temperature, number one source of degradation. But as they've gotten better and better and better at making solar panels, dual glass modules, bifacial modules improved the performance of solar panels pretty dramatically, just because they eliminated the backsheet, and the backsheet was one of the sources of degradation, water ingress through the backsheet. Well, when you went to glass, that stuff mostly went away. So, but there was another variable that glass enhanced. It's called microcracking. Microcracking was a big problem. It was one of the sources of accelerated degradation. They go to glass, a lot of this microcracking stuff reduced. Well, what's going on? Well, when you sandwich the module between the 2 points, it changes the position where the module, or where the wafer is at the deflection point in the module. Well, microcracking, when they started really looking at that, it turns out if you are able to reduce microcracking as a natural characteristic of a solar panel, you can reduce its degradation. If you put a solar panel up on a rack up in the wind and it's flopping around in the wind all the time, you're going to induce microcracking. Versus if you put it flat on the ground, there is no wind. There is no effective wind that influences the solar panel. It's one of the reasons we can go to 194 mile an hour wind zones. So the function of microcracking drops dramatically. There's one other function that drops: differential soiling. This is another key variable that Erthos effectively eliminates, because we clean the panels every day with a robot that goes out and sweeps all the dust, sweeps off the differential soiling. Bird poop is a good example. If bird poop lands on a solar panel, there's a hot spot right under the bird poop. And that hot spot causes the microcracks to propagate and causes other problems over time. Well, solar panels are all spread out. Some of them get bird poop, some of them get a little bit of dirt on it and other parts and pieces. Some of them are a little more microcracked than others. So you'll get differential degradation from one module to the next, which causes intra-string differential in degradation and further causes degradation to happen in the plant. So there's a whole bunch of versions of things that get reduced by setting it flat on the ground. You're able to clean it, reduce differential soiling. There is no wind. Microcracking goes away. And this is the last one, it's fascinating. When you're up on a rack, as the temperature goes up and down, it goes, cloud goes in front of the sun, that temperature changes quickly. A thermal change, rise and fall of the solar panel itself happens fairly quickly. When it's sitting flat on the ground, as it turns out, the temperature of the modules slowly rise and slowly fall because there's a heat sink that they're connected to. And that rate of rise and fall of thermal is actually less damaging to things like microcrack propagation. So it's a whole litany of things. These are hard to prove. Only time really does that. And now we have projects that have enough time to show it. And it's quite powerful. The outcome is quite powerful. So,
I mean, we might expect 0.5%, 0.4 to 0.5% degradation in modules per year. You know, when you look at the output from an array, it's just slowly ticking down. You still have 80% plus productivity at the end of 25 years.
20 years.
What is the expectation with Erthos, or what are you learning from the field so far about degradation?
So we modeled 0.5 in all of our plants, and we haven't changed that. That's still the standard assumption. It would be fair and reasonable to model 0.4 just based on what we've seen. Given another year or two of performance data in the field, actual life performance data, I believe that that number is going to come down to 0.3-ish. But it's really interesting because there's degradation, individual module degradation, but then there's differential degradation from one module to the next. And that mismatch degradation actually has a bigger effect over time. And that's where I think our biggest influence comes. Rather than just the absolute degradation of one module, it's the spread of degradation from across 100 modules. What's the one with the most to the least? The modules in an Erthos plant will degrade very close to one another, whereas ones on a tracker will degrade in a larger spread or distribution. And I think that has the single biggest effect, is the time-based change of differential degradation will prove out to be the biggest benefit from a degradation perspective in solar panels with Erthos.
Very well. Well, we're almost out of time. I hearken back to my conversations with Matt Campbell, who's the CEO of Terabase Energy. One of the things that he points out is we as an industry are chasing penny per kWh solar electricity. That unlocks mass green hydrogen, for example. When you think about the future of large-scale solar, what are some of the things besides interconnection, that you see as the biggest challenges or opportunities for us as an industry?
So I'm a very firm believer that we are not going to electrify our way out of the problem. It's not possible. We don't have enough time to electrify our way out of the problem. The US grid would have to get 2.5 times bigger than it is today if you want to change all the automobiles to electric. And that's just it's not viable. So we have to solve the problem another way. We have to find a replacement for fossil fuel. I'm 100% firm believer that hydrogen is that replacement. It's the right fuel to replace fossil fuel. It's just too expensive. That's just the bottom line. So the introduction of the IRA was targeted to drive that price down. And that's happening. So you're seeing all kinds of projects being announced. The cost of the input electricity to split the hydrogen into, or split the water into hydrogen and oxygen is everything. It's a huge component variable. Erthos levelized cost of energy in certain low geographies will be somewhere in the vicinity of $25 to $26 a megawatt hour compared to a single axis tracker with a First Solar or a crystalline silicon bifacial. That'll be $31, $32 a megawatt hour. Everything apples to apples. Those are, Lazard variable LCOE. You have to get to below $20 a megawatt hour. And there are ways to do that. There are ways to get to below 20. If you take away interconnect, that's a significant impact. And then you look at some of the other variables that impact the cost of a solar plant. Financing costs of a solar plant are huge. One of the biggest single risks on any solar installation is you've got a single offtake. You got one contract with one PPA, and then what happens when that PPA is done and you want to do a merchant plant? What's the projected merchant value and so on and so forth? Those risks cause the financing to extend out, and that financing cost is a significant variable. When you go to hydrogen, hydrogen produced from solar at the energy hubs, as they're describing, right? They're talking about hydrogen hubs all around this part of the country. The offtake of those hydrogen hubs, there will be multi-dimensional offtakes, lots of different types of offtakers, not just one. And that construct will help lower the cost of financing for those assets because you'll have many offtakers. And the competitive product is brown hydrogen or hydrogen from fossil fuel, or it's fossil fuel itself for purposes, for combustion, for transportation or otherwise. Since that becomes your competitor, you're no longer just competing with solar, you're competing with that product. And as long as you're able to produce a product that's cheaper than that product, you'll always have an offtake. And that, again, influences the financing and the economics of the project. So hydrogen is here, it's ramping. All the beneficial reasons, no interconnect, multi-party PPAs to reduce risk. Development cycle times can be very, very short. Rather than 4 and 5 years development cycle time, you can actually go to execution in a year, from the land development perspective. We're going to be bound by the supply chain. That's going to be the constraint. Supply chain of electrolyzers, supply chain of polysilicon. And bringing those into the United States, supply chain of electrolyzers and supply chain of polysilicon is absolutely everything for the future of hydrogen in this country. And we'll talk about it in some future podcasts, what are some of the things that Erthos is doing on that front. But I'm a firm believer that that's the future of the industry. And when you do that, when you disconnect us from the grid, solar will grow asymptotically for several years. It will ramp into the, I think we've got 150 odd gigawatts installed since the inception of time for solar, doing 23, 24 gigs a year. We will get up into the 50, 60 gigs a year once we get hydrogen happening and disconnect from the grid. So
I love
a
it.
lot more on that subject, though.
I love it. Just going around the interconnection altogether, building a power plant that produces hydrogen from green electrons. Well, thank you so much, Jim Tyler, CEO of Erthos. How can our listeners find you?
Oh, go to the website, erthos.com. That's the best place. Certainly we're heavy on LinkedIn. But our general customer base is the developers. That's who we sell and market to. And I know there's quite a few of them that have been looking at us. So but getting in touch, listening to Clean Power Hour with you, I think is a very good source of them starting to pay attention. Listen. Good stuff.
The Clean Power Hour is brought to you by DinoWatts. If you're a solar PV asset manager or performance engineer, you need better data and better business intelligence. With DinoWatts digital twin benchmarking technology, you get more accurate, efficient, and faster performance measurement results. The 4th generation Dino recently completed a technical review by DNV. You can download the report at dinowatts.com. That's DENOWATTS.com. Now back to the show. You can find all of our content at cleanpowerhour.com. Give us a rating and a review on Apple and Spotify. Subscribe to our YouTube channel. And most importantly, tell your colleagues about the show. That is the greatest way you can help the show and help others find the show. I want to thank Jim Tyler for coming on the show today. Look forward to seeing you in Vegas at RE Plus. This episode will drop prior to that. So we're going to Vegas September 11 to 14. Erthos will be there. The Clean Power Hour will be there. And you can meet up with us there. So with that, I will say, let's grow solar and storage. Take care, Jim.
Thank you, Tim.
Hey, listeners. This is Tim. I want to give a shout out to all of you. I do this for you twice a week. Thank you for being here. Thank you for giving us your time. I really appreciate you and what you're all about. You are part and parcel of the energy transition, whether you're an energy professional today or an aspiring energy professional. So thank you. I want to let you know that the Clean Power Hour has launched a listener survey, and it would mean so much to me if you would go to cleanpowerhour.com, click on the About Us link, right there on the main navigation. That takes you to the About page, and you'll see a big graphic, Listener Survey. Just click on that graphic, and it takes just a couple of minutes. If you fill out the survey, I will send you a lovely baseball cap with our logo on it. The other thing I want our listeners to know is that this podcast is made possible by corporate sponsors. We have two wonderful sponsors today, Chin Power Systems, the leading three-phase string inverter manufacturer in North America, and Dynawatts, a performance monitoring platform for utility scale solar. So check out CPS America and Dynawatts. But we are very actively looking for additional support to make this show work. And you see here our media kit with all the sponsor benefits and statistics about the show. You know, we're dropping 2 episodes a week. We have now over 320,000 downloads on YouTube, and we're getting about 45,000 downloads per month. So this is a great way to bring your brand to our listeners, and our listeners are decision makers in clean energy. This includes project executives, engineers, finance, project management, and many other professionals who are making decisions about and developing, designing, installing, and making possible clean energy projects. So check out cleanpowerhour.com, both our listener survey on the About Us and our media kit, and become a sponsor today. Thank you so much. Let's grow solar and storage. The Clean Power Hour is brought to you by CPS America, the maker of North America's #1 three-phase string inverter, with over 6 gigawatts shipped in the U.S. The CPS America product lineup includes three-phase string inverters ranging from 25 to 275 kW. Their flagship inverter, the CPS 250-275, is designed to work with solar plants ranging from 2 megawatts to 2 gigawatts. The 250-275 pairs well with CPS America's exceptional data communication, controls, and energy storage solutions. Go to chinpowersystems.com to find out more.